In this screencast, we're going to look at the equation for the tension in a belt, and in this screencast we're going to make the allowance for a centrifugal tension also. So if I have a belt going around a pulley, I'm going to just look at a little small section of it here, a really small section here. And I'm going to assume that the mass of the belt is equal to m0 kilograms per meter. So it could be 1 kilogram per meter or 2 kilograms per meter, something like that. So that's this value m0. We know from physics that the centrifugal force is equal to mv squared over r. So this would be the total mass of the belt. So if I'm looking at it for a particular section, it's the mass per kilogram, and I need to know what is the distance. Okay, so what is this distance here? And we know that that distance is the radius times the angle in radians. So r times d theta. So this distance here will be r times d theta. So multiplying the distance by the by kilograms per meter gives me the kilograms. So that's the mass over v squared over r. The r's will cancel out each other. So my centrifugal force is m0 v squared d theta. So we just have to remember that for a minute or two, and we'll come back to it. Now when I'm looking at the pulley, and I'm looking at the angle theta, this small angle, it can be split up into two components. And this is the reaction force N, and there's a friction force. And this reaction force N, some of it will be taken on this side and some on this side. So there's a tight side and a slack side on the belt. So if we're pulling, actually this is wrong, so I'm going to cancel this. So in this screencast we're going to look at the effect centrifugal tension has on the power transmitted by a belt. Okay, so we're going to look at a belt, and we're going to look at a small section of it here, so this small section over here. And centrifugal tension is equal to mv squared over r. But the belt we're going to consider, it has a mass of m0 kilograms per meter. So if I want to get the mass in kilograms, I have to know the distance. So we can get that distance there by multiplying the angle d theta by the radius r. So m0 r times d theta will be the mass. So this is the kilograms per meter multiplied by the distance here in meters gives me the mass times v squared over r. And the r's will cancel out, so the centrifugal force is m0 v squared times d theta. Okay, so normally on the belt we will have a reaction force. So as the belt turns in this direction, we get a tight side and a slack side. We have a tension T plus d theta over here, and a tension T here. So that tension can be broken into its horizontal and vertical components, and the vertical components of this and this must equal to this reaction force N. So if this is our angle theta, we can split that into half. This is actually that should be d theta. This the angle then d theta is over 2, and this is the angle d theta over 2. So the sine of this is equal to the vertical component over t plus d theta, and similarly over here the sine of this angle is this component over t. So we have them down here then. So taking this side, t times sine d theta over 2. Okay, so that's the hypotenuse. T times sine of this is this component, plus t plus dt times sine d theta over 2. So that's the hypotenuse here. The sine of this angle gives me this component. So this plus this is equal to my reaction force N. Okay, if I assume that this angle was very small, d theta over 2 is very small, the sine of a very small angle in radians is equal just to the angle in radians. So this sine d theta over 2 just becomes d theta over 2. And similarly over here. So I can see I have t times d theta over 2 and I have t times d theta over 2 here. So that's 2t plus d theta over 2. And I'm just going to multiply that out. And here I got a really small number multiplied by a really small angle. So it's very small number multiplied by a very small number is something very small, and we're going to assume that's equal to 0. Okay, so that disappears, and 2t times d theta over 2 just becomes d theta. Just becomes t d theta. So my value for n becomes t times d theta. Okay, so we're just going to store that number over here. Okay, I did mention that the centrifugal force was m0 v squared times d theta, and we haven't allowed for that in this formula here. So there's my centrifugal force. So the actual total reaction is this plus this guy here. So this this force, so let's say it's due to the centrifugal tension. And the centrifugal tension will be the same on both sides. So if I take here, so the centrifugal force, so this guy, Fc, centrifugal force over 2, because it's this plus that, is equal to centrifugal force, so this is half of it. So the sine of this angle is the opposite over hypotenuse, and then I can rearrange that equation. We said that the sine of a very small angle in radians is equal to just this very small angle. I can bring the TC up, and then I can multiply both sides by 2, and the 2's will cancel, and I get an expression for the centrifugal force. But I already had an expression for the centrifugal force, so then Tc times d theta must be equal to m0 v squared times d theta. Okay. The d thetas then cancel out. So I have an expression here for the centrifugal tension. We will use that in another video. Okay, I'm bringing this guy down. I have an equation for what n is. So t times d theta was equal to m. Well, that was this old force. But I now have to allow for my centrifugal force. Okay, so it's now n plus this centrifugal component here. So my t times d theta is equal to n times. So instead of centrifugal force, I'm going to say it's Tc times d theta. So I bring Tc times d theta across here, so we get T minus Tc times d theta, and that's equal to n. Okay. So that's something that we're just going to store in the background for a while. So the total reaction force up here now is equal to this expression here. Now if I look at the horizontal components, if I take this side first, so there's my tension T. So T times the cosine of d theta over 2 is equal to this angle, and T plus dt times the cosine of d theta over 2, so this guy here, is equal to this value. And when we add that to their frictional force, which is mu times n, now n is now this value, then the total forces going in this direction must equal to the total force going in that direction. So I can say t times cosine dt over 2 plus mu n. So this plus the green is equal to t plus dt times cosine dt over 2. But there's the equation here. If this is a really small angle, the cosine of a really small angle is 1. And similarly over here. So this just becomes t plus un. So t plus mu n is equal to t plus d theta. And the two t's cancel out either side. So I have an expression for the friction there. Mu n is equal to dt. Okay. So mu n is equal to dt, and we have n is equal to t times d theta. So mu n, well, n was equal to t minus tc times d theta. That is equal to dt. So if I bring the t minus tc over to this side, I get mu times d theta equals dt over t minus tc. So I want to integrate that over the full length of the pulley. So it goes from 0 to theta and from t1 to t2. So if I let u is equal to t minus tc, then du dt is equal to 1. This is just a constant in this sense. So du is equal to dt. So my integration becomes the integral of mu dt over 1 over u times du. And when I integrate that, I get u times theta is equal to the natural log of u. And that becomes the natural log of t minus tc between the limits of t1 and t2. Okay, so instead of t, I'll put in t1 minus t2 times tc. Rule of logs, the natural log of a minus the natural log of b is equal to the natural log of a over the natural log of b. And if I get the anti-log on either side, I get an expression e mu theta is equal to t1 minus tc all over t2 minus tc. That is our new expression for flat belt drives, including the centrifugal tension.